This video is part 2 of Chapter 10, Quasi-Experimental Designs and Program Evaluation. We're going to continue to talk about some of the issues that are related to threats to internal validity. The next one is called subject attrition. And basically, when we lose participants over time, over the course of a study, we may lose some of the qualities of equivalency across different groups that we had at the outset. So in natural environments, let's say you're in a workplace and you want to test the effectiveness of a program in your workplace, you may randomly assign participants to groups, or even without the random assignment, you may select some people to participate. But over the course of time, some of them drop out and don't continue to participate. So what you have is a problem of, if you're treating groups differently to manipulate your independent variable, what if the dropout is different across your groups? And that creates a great deal of trouble. The difference between the treatment and control group could have been due to naturally occurring differences in who sticks in the study and who doesn't. So it just adds additional potential causal variables to your situation. For example, if an experimental treatment, like this happens fairly often in workplace health interventions. So let's say you recruit a bunch of people to be in an exercise program at the workplace, with the goal of, maybe reducing some of your health-related insurance costs. So you recruit people, you get them on board, but what if the workout regimen that's been selected is hard? You're going to lose participants, and the ones who stay are the ones who were already more fit to begin with. So, you have some competing influences. It may not be your program at all that's leading to better health outcomes. It may have been that only the healthiest persisted in the program. So for example, if you have an exercise program that's offered to employees who want to lose weight, and they sign up, these are very common programs in workplaces these days. At time 1, you've got 50 participants. Their average weight of all the participants is 225. At time 2, you're down by 50%. 25 of the participants drop out. And at time 2, the average is 150 pounds. You might at first glance say, wow, that's a huge weight loss. This is a really effective program. Well, like I was saying earlier, if the exercise program is intended to help people lose weight, it may be seen as a struggle. It may be seen as aversive. It may be seen as painful. So if you lose half your participants, the ones that remained may have already been healthier. They may have been slightly lighter, so they may have weighed less initially than that average represents. An average, people are going to vary around that number. So you're losing that many participants. You can't really determine whether it is their individual characteristics like persistence that may be explaining it and have nothing to do with the program itself. So you can't answer this question, did the exercise program help or not? Selection is a different kind of problem. This happens when the individuals who end up in the treatment and control groups at the start of the cover of the study, they were initially different. Now, random assignment takes care of this, but if you're in a naturally occurring environment, you may not be able to randomly assign people to anything. They may be naturally existing groups. If you miss something that's different about them, you don't do pre-testing, for example, or the pre-testing measures that you use aren't sensitive to a particular difference you weren't expecting, you may end up with a selection effect. These differences then can become an alternate explanation for any effects that you observe. Now, in a true experiment, random assignment would take care of this. But as I said, you can't always do that. So for example, an example of a selection effect, you may have, you're trying to test a community recycling program, and individuals who are interested in recycling are encouraged to participate. And you want to compare the weight of garbage, i.e. not recycled trash, from participants in the program with the weight of garbage from people who are not in the new program. So you have individuals who are interested in recycling who've been encouraged to participate in the program. They may already be coming in with some pre-existing attitudes and values that change their trash to begin with. So maybe they're buying more products that have recyclable materials in them or with less materials in packaging than the people who are in the non-equivalent comparison group because they're not in the new program. They weren't choosing to be in the program. So you may have a selection bias. You cannot determine that this difference that you're observing between those not in the program and those in the program is due to the program. It may just be due to who signed up for the program already being people who produce less trash. Now, additive effects are when you have two of these threats simultaneously. So if you have a selection effect, you have groups that are not formed by random assignment, you have some possibilities of these additive effects. You could have, for instance, selection plus maturation effects. You could have selection plus a history effect. You could have selection plus an instrumentation effect. So as a researcher, when you're dealing with the natural world, with the real world, there's a lot of messy things there. And that means you have to really keep your eye on these other potential competing causal explanations when you interpret your data. It may be frustrating, when you hear scientists talk about their findings. You can tell the good scientists because they're the ones who really qualify their findings. They say, now you need to keep in mind there's this factor and this factor and this factor and this factor. And what they're usually talking about are threats to internal validity. An example of additive effects with selection, if you have two schools, School A and School B, let's say that School A starts an alcohol prevention program or alcohol abuse prevention program at week 4. The DV is how many alcohol-related infractions in the residence halls. School B, that doesn't have the program, is the comparison group. Let's say at week 4, the newspaper at School A, there's an event on campus, an unfortunate event. You have a student death due to alcohol intoxication. So that's a local history effect. Can you say that the program was effective? No, you can't. Now, these lines, School B is this upper line, School A is this line. My color effects are a little off in my PowerPoint. So School A is the line where you show this precipitous drop, whereas School B is the jagged line at the top. Week 4, you have simultaneous things happening, implementation of the program and the student death. This precipitous drop could be just an artifact of the fact that the sad event of a student death has occurred and people have avoided alcohol use as a result of that historical event. It may or may not have had anything to do with the prevention program. With these threats to internal validity, the bottom line is, without a comparison group, and that's what happens a lot of the time in these natural environment type studies, is if you don't have a comparison group, i.e. a control group, you have to deal with history effects, maturation effects, and so on. When you have even when you have a comparison group, though, there are still threats to internal validity. You have selection effects, you have differential regression effects, you have additive effects that can pile on to selection effects. So what your authors are trying to say is there are always going to be threats to internal validity, and as a good researcher, you're going to always be on the lookout for them, and you're going to do everything you can to minimize the threats to internal validity without harming the integrity of your study. There are some threats that even the best controlled true experiment can't eliminate entirely, and there are many of them. There are expectancy effects on the part of the experimenter and so-called novelty effects, like if you are exposing your participants to a type of task that they've never seen before or an experience that's brand new to them. Contamination is another type of threat to internal validity. It involves information, kind of clues, if you will, that gets communicated between and among participants. So let's say that I'm collecting data across a month-long period of time, and there's an experimental manipulation, and some of the subjects who've been participants in the first week start spreading word about what happens in the experiment. And once that word gets out, then the new subjects know what to expect. If that happens, it can create expectancies on the part of the participants. It can create kind of all kinds of negative impacts, especially if you've used deception of some kind. It can lead to hostility directed at the researchers, or just refusal of people to participate. More subtly, it may dilute the impact of your independent variable manipulation. Experimental or expectancy effects happen when pre-existing biases on the part of the experimenter, either just because you didn't know that you had expectancies, or even if you knew you had them, you thought you had them under control, they can influence the results of the study. Novelty effects, your authors describe the Hawthorne effect, where you have changes in people's behavior simply because they're exposed to something new. So let's say you have a new program. So let's say you have a new program that involves playing some games, and you're hoping to, by having these recreational activities, to improve empathy. Thinking off the top of my head, maybe the games and stuff are fun at first and people get along better as a result, but once the novelty of the game playing wears off, perhaps there's no effect on the dependent variable of interest. There are also threats to external validity. You may have treatment effects that you can demonstrate in a true experiment, but beyond the particular people who were involved in your original experiment, the treatment may not generalize, and therefore you won't see that same outcome. This can happen, for example, if you've run your experiments using, let's say, college students as your subject population, and you find an effect of your independent variable manipulation. But then when you take it out into the world and you're testing with people who are significantly older, with different experiences and different backgrounds, you find that your finding just doesn't hold up. So that's a threat to external validity, where you have a very homogeneous, maybe not age-diverse population that you have access to, and it's just too different from the population you're actually interested in. when you test the finding in the real world. To look at some more of these threats to external validity, random sampling is one of the best ways to create representative samples. But what we know for sure is that we rarely have the ability to actually do random sampling. And that may surprise some of you. Psychology research, if you look at all of it, the vast majority of the research done in psychology involves questionnaires and surveys. We often don't have the ability, either practically, sometimes ethically, to do random assignment in experiments. We often end up using convenience sampling and basically taking all comers, whoever volunteers to be participants in our studies. We have to be aware as researchers of the way in which various uncontrolled for factors may come out of the fact that we have particular groups of participants at any given time and place. And they may have unanticipated uniquenesses that have an impact on our dependent measures of interest. The best way to deal with this is to do replication, and do replication intentionally. And by intentionally meaning you're going to do several waves of the same study, collecting data in batches, and then you compare the results versus one another. And another expansion of that is to do your replications in more than one location with more than one source of subjects. So you can replicate at the same university with the same group of college students over and over, and not surprisingly, you were likely to get the same result. If you replicate at different universities in different locations, and then stretch beyond that to different types of samples, then you have more chances of showing that you have a robust effect. So these issues related to external validity are best dealt with by replicating your study with various kinds of participants from different locations. You may want to vary the types of independent variable conditions so that you're able to show greater robustness and a refined ability to kind of tease apart differential effects, and you want to vary by time. Now we're going to shift gears a bit and talk about this type of research called quasi-experiments. I mentioned before, quasi, I always tell my students quasi means sort of, or it's experiment-like. Quasi-experiments, they involve the manipulation of an independent variable and a comparison group. But what you don't have is the kind of control over random assignment that you would have in a true experiment. The lack of randomization is like the major characteristic of quasi-experiments. This is often when you have groups of participants that you're going to compare, and they're in the groups that they belong to because they already have some trait or attribute. Think of the classic example of doing sex differences research, where you compare groups of people who are different based on their biological sex. Quasi-experiments, you still want to know, is my treatment, is my manipulation of the independent variable effective? But they're done when a true experiment isn't possible. So the example I just gave you, you can't randomly assign people to be either to have a particular biological sex. It's just not possible. You also can't randomly assign people to be, say, native speakers of Spanish. That's not ethical and it's not feasible. So you may have these natural differences between people that represent an independent variable of a sort. I call them subject variable independent variables. and you want to compare those groups, but you can't do a true randomization in that context. This does create some problems of interpretation because you can't go to the same level of being able to rely on the independent variable, which would be the differences between subjects. You can't really go there and say that is the cause. There may be other interacting variables, separate variables that influence your behavior of interest. But what you can do is maximize the degree to which you can isolate your independent variable of interest. So that's why we call them quasi-experiments. You're using basic experimental methodology without the ability to randomize. Now, when I found this graphic, it doesn't come from your text, but I found it useful. When you think about the rigor of an experiment, what you're really talking about is your ability to make causal inferences after you get your results. In non-experimental group research, where you're just doing a pre-post test, for example, you take everybody, all participants get the intervention, and you measure them at one point in time, and then you measure them at the second point in time. In that case, you don't have a comparison group. You may have a baseline measure, and then you have a post measure. That's less rigorous than a quasi-experimental design, where you have a one group of participants that gets the treatment, and the other group does not. So you have a comparison group. Then, if you want to increase your rigor even further, you can use the example of a randomized control trial, where you have randomized your participants to different treatment and control groups. You've made sure that they were initially equivalent by doing so, and then you do your intervention with your experimental group, but not with your control group. So when we think about these different methodologies, you have the non-experimental technique, the quasi-experimental technique with naturally occurring groups, and the randomized control trial, where you are able to randomly assign people to groups, and by doing so create initial equivalence. This one group pre-test, post-test, that's what on this slide they were referring to, because it's different authors, they were referring to that as non-experimental. Your authors call it the one group pre-test, post-test design, which is a mouthful. They also label it, I don't know if this is necessarily necessary to call it a bad experiment or a pre-experimental design, but some people do. It's a simple non-experimental design is what it is. You take an intact group, and your authors give you the example of a classroom of children or a group of employees, and you implement an intervention. So this O1 x O2, pretest is the first observation, that's O1, treatment is implemented, that's X, post-test is the second observation, or O2. So what you have here, I would look at this as a pilot study. So I have a classroom, I have a reading intervention. I want to see how it works. So I take one group of students, I have them do the intervention, and then I look at their performance. If I see the possibility of improvement based on the intervention, then I would take the next step and do a more controlled quasi-experimental test. The reason why I would need to take that second step is because you don't have any control over the various threats to internal validity. Any change from pre-test to post-test is vulnerable to all those things we've already talked about: history, maturation, instrumentation, and so on. So I could only look at it as, if I see the effect in the predicted direction, I could say to myself, that's interesting. Now we do the real experiment. So I would look at it as a pilot, maybe a proof of concept test. The non-equivalent control group design is when you take one group and have the intervention for them, but not the other group. So you have two separate groups. Typically, they're going to be naturally occurring groups. You're not randomly assigning necessarily. Actually, you're not randomly assigning, period. And you then compare. So they're non-equivalent because you're not randomly assigning them to groups. So you haven't established that you have initial equivalency between the two groups, but you do have a comparison group or a control group. If the two groups are similar in their pretest scores and they differ in their post-test scores, then you can have more confidence than in the previous example of the non-experimental technique that the intervention had some kind of effect. Now, the trick is, if you show at pretest, so observation 1, at time 1, if you show that the means, say, the mean reading score is the same between these two groups, but you haven't randomly assigned them to these groups, nor do you have a lot of control over other kinds of experiences that these two naturally occurring groups might have, and you then see a difference in performance at time 2, you have some challenges because you haven't had the ability to control all of those factors. If you want to make a claim about the effect of the treatment, you need to know that there's a group that's like the treatment group that can serve as a comparison. So you have to identify a roughly equivalent group. In some circumstances, that's more possible than others. And you may have to take advantage of the convenience of that. So let's say I'm interested in second grader reading, and I'm in a school system, and there are lots of second grade classes, and they have a curriculum that's pretty rigorous and similar across teachers. So every teacher is basically teaching the same exact curriculum. If I know that, then I can have more confidence that if I do an intervention with one set of classes, but I don't do the intervention with the other set of classes, that rough equivalency between them sets me up better for comparison than, say, if I don't know that they're using all the same curriculum. Now, I haven't randomly assigned, so I haven't created equivalent groups initially on a whole host of unforeseen variables. But I have done more than I was doing in the non-experimental technique. You still have some threats to internal validity. Let's say just by accident, this group that didn't have the intervention, let's say by accident their teacher was absent for a total of 4 days and they had a sub, whereas this group, their teacher was never absent. It could be just the fact that their teacher was absent that caused their performance to be lower than the intervention group who received the reading intervention. So you still can't control for things like history in this type of design. So just to reinforce what we were looking at in the last slide, I provided you with this image. You've got time 1 is the pretest, time 2 is the post-test. The only difference between the two groups in terms of method is which one receives the treatment or the intervention. The other group is the non-equivalent control group. And that concludes part 2 of chapter 10.